Imagine standing on a clear night, gazing up at the brightest object in the sky after the Moon and Venus, a colossal, swirling giant that has captivated humanity for millennia. Jupiter, the king of our solar system, is more than just a beautiful sight. It's a world of extremes, a planet so massive it could swallow every other planet in our system and still have room to spare. But beneath its vibrant bands of clouds and that iconic great red spot lies a realm of mysteries that even our most advanced probes and telescopes have barely begun to unravel. For centuries, Jupiter has been both a beacon and a puzzle. Its immense gravity shapes the orbits of nearby worlds, acting as a cosmic shield that deflects asteroids and comets away from Earth. Yet, despite its protective role, Jupiter remains one of the least understood planets in our neighborhood. We've sent spacecraft like Voyager and Juno to study its storms, its magnetic fields, and its hidden interior, but every answer we uncover only leads to more questions. What powers its furious winds, racing faster than a speeding bullet? What lurks beneath its dense, turbulent atmosphere? And could there be secrets within its moon system that challenge everything we know about the potential for life beyond Earth? Today, we're diving deep into the 25 most baffling enigmas of this gas giant phenomena that defy explanation and ignite the imagination. From bizarre lightning storms 1,000 times more powerful than anything on Earth to the eerie radio emissions that pulse like an otherworldly heartbeat, Jupiter is a treasure trove of cosmic riddles. Some of these mysteries could rewrite the textbooks on planetary science, while others might hold clues to the very origins of our solar system. So buckle up, because by the end of this journey, you'll never look at Jupiter the same way again. One of the most striking features of Jupiter is that colossal, swirling tempest we call the Great Red Spot, a storm so vast it could swallow Earth whole, and yet it's been raging for at least 400 years. When astronomers first trained their telescopes on Jupiter in the 1600s, they recorded this massive crimson vortex, but what keeps it going? On Earth, even the most powerful hurricanes fizzle out after weeks, their energy sapped by friction with land and ocean. Yet here's Jupiter's enigmatic storm, defying time itself, churning endlessly in a planet with no solid surface to slow it down. Scientists suspect the storm draws energy from Jupiter's chaotic atmosphere, where jet streams scream at speeds over 400 miles per hour, feeding the vortex like rivers pouring into a whirlpool. But here's the puzzle. Those same winds should have torn the storm apart by now. Some researchers think the Great Red Spot digs deep, tapping into heat rising from Jupiter's hidden interior, while others argue it merges with smaller storms, constantly renewing itself like a cosmic engine. Then there's the color, why red? Some say it's chemicals like sulfur or phosphorus being dredged up from below, but no one knows for sure. Even stranger, the storm is shrinking. Centuries ago, it might have been 3 times wider than it is today. Is it dying or just changing? Recent data from the Juno spacecraft reveals the storm stretches deeper than expected, plunging over 200 miles into Jupiter's atmosphere. That could explain its stubbornness. It's not just a surface feature, but a towering root system of violence. Yet for all our advances, we're still left wondering, will this ancient tempest vanish in our lifetimes, or will it outlast us all? A perpetual mystery swirling in Jupiter's clouds. Beneath Jupiter's swirling clouds and violent storms lies a mystery that challenges everything we thought we knew about how gas giants are built. For decades, scientists assumed Jupiter had a solid core, a dense, rocky heart buried under layers of hydrogen and helium, like a seed at the center of a cosmic fruit. But when NASA, a Juno spacecraft, began measuring the planet's gravity field, the data told a very different story. Instead of clear evidence of a compact core, Juno revealed something far stranger, a core that might not be solid at all, but a fuzzy, diluted mix of heavy elements blending indistinctly into the surrounding gas. This discovery sent shockwaves through planetary science. Traditional models suggested gas giants form when a solid core, about 10 times Earth's mass, grows large enough to pull in vast amounts of gas from the surrounding nebula. But Jupiter's blurry, diluted core throws that idea into question. Some researchers now think Jupiter's core could have been eroded over billions of years by extreme pressures and temperatures, dissolving like a sugar cube in hot tea. Others propose it might have never been fully solid to begin with, instead forming through a chaotic process where heavy elements swirled and mixed with gas from the very start. The implications are enormous. If Jupiter lacks a traditional core, it could mean we've misunderstood how not just gas giants, but entire planetary systems take shape. Even more puzzling, Juno's data shows the core, or what's left of it, might be lopsided, with more heavy elements concentrated in one hemisphere than the other. How does a planet end up with such an uneven interior? Could a colossal impact have scattered the core early in Jupiter's history? Or is this asymmetry a clue to how material was distributed in the young solar system? Every theory comes with its own hurdles. A dissolved core would require unimaginable heat and turbulence deep inside Jupiter, while a fuzzy, primordial core challenges our ideas of planet formation. Meanwhile, alternative models suggest Jupiter might still have a solid core, but one shrouded in a thick layer of metallic hydrogen, making it invisible to Juno's gravity measurements. Until we send more probes or develop new ways to peer beneath those churning clouds, the truth about Jupiter's heart, or lack of one, remains one of the most tantalizing unsolved puzzles in planetary science. Jupiter's northern and southern lights put Earth's auroras to shame, glowing curtains of light so intense they could outshine our sun, while our planet's auroras paint the sky with delicate greens and purples. Jupiter's blaze with X-rays and ultraviolet radiation, unleashing energy bursts powerful enough to briefly outshine the entire planet. But here's the twist: these auroras shouldn't exist, at least not the way they do. On Earth, solar winds, charged particles streaming from the sun, collide with our magnetic field, sparking the light show we know and love. Jupiter, though, is so far from the sun that solar winds are weak. So what's fueling these monstrous displays? The answer might lie in Jupiter's own backyard. Its volcanic moon, Io, spews tons of sulfur and oxygen into space every second, creating a donut-shaped cloud of plasma around the planet. As Jupiter spins, a full rotation every 10 hours, its monstrous magnetic field, 20,000 times stronger than Earth's, slingshots these charged particles toward the poles at nearly the speed of light. The result, auroras that never fade, dancing in ultraviolet and X-ray wavelengths, invisible to our eyes but detectable by telescopes like Hubble and the Chandra X-ray Observatory. Yet even this explanation doesn't cover everything. Some of Jupiter's auroras pulse independently of solar activity, flickering like a candle in a cosmic wind. Others, bizarrely, appear at the planet's equator, something never seen on Earth. Scientists suspect hidden electrical currents surging through Jupiter's metallic hydrogen interior might be juicing these anomalies. Then there's the mystery of the dark auroras, strange blackouts where the lights vanish entirely, as if someone flipped a switch. Could Jupiter's magnetic field be tangling with unseen forces, or is there some exotic physics at play we haven't even imagined? One theory points to Jupiter's other moons, Europa and Ganymede, whose icy surfaces may be shooting plumes of water vapor into space, adding fuel to the auroral fire. Another wild idea suggests Jupiter's own rapid rotation generates colossal electric fields, acting like a particle accelerator on a planetary scale. Whatever the cause, these auroras are more than just a light show. They're a window into the chaotic, high-energy playground of Jupiter's magnetosphere, where the rules of space weather seem to rewrite themselves daily. What's clear is that Jupiter's auroras aren't just scaled-up versions of Earth's. They're a phenomenon entirely their own, a violent ballet of particles and magnetism that defies our best models. And as long as they keep glowing, scientists will keep watching, piecing together the secrets of this radiant, untamed world. Among Jupiter's swirling bands of clouds, there are eerie gaps, dark, almost window-like patches where the planet's deep atmosphere seems to peel back, revealing warmer layers beneath. Scientists call these features hotspots, but the name barely scratches the surface of their strangeness. Unlike Jupiter's stormy chaos, these regions are eerily calm, with barely a cloud in sight. Yet they radiate heat like cosmic vents, defying every expectation about how gas giant atmospheres should behave. What makes these hotspots so baffling is their unpredictability. Some vanish within weeks, while others linger for years, drifting slowly across Jupiter's equatorial belt. Even more confusing, they're not actually hot in the way we'd expect. While they're warmer than the surrounding clouds, they're still colder than Antarctica, clocking in at around -150 degrees Fahrenheit. So why call them hotspots? Because compared to the bone-chilling temperatures of Jupiter's upper atmosphere, these patches are like oases in a frozen desert, emitting infrared radiation that telescopes can detect from Earth. The real mystery lies in how they form. Most atmospheric models suggest Jupiter's weather should be uniform, with clouds and storms distributed evenly. Instead, hotspots appear like sudden holes in a blanket, breaking all the rules. One leading theory suggests they're created by descending air, like atmospheric sinkholes where dry gas plunges deep, stripping away clouds and leaving behind these barren windows. But that doesn't explain why they're so localized, or why some vanish without a trace while others stubbornly persist. Even stranger, these spots seem to be linked to Jupiter's lightning, or rather the lack of it. While the planet's stormy regions crackle with bolts 1,000 times stronger than Earth's, hotspots are eerily silent, almost as if the atmosphere itself is holding its breath. Some researchers think this silence is a clue, hinting at a lack of water clouds in these zones, which are crucial for generating lightning. Others suspect these patches might be gateways, funnels channeling energy from Jupiter's scorching interior up into the cooler outer layers. Then there's the wild card, the Great Red Spot. Recent observations show hotspots sometimes cluster near the storm's edges, as if the giant vortex is somehow herding them. Could Jupiter's most famous tempest be shaping these enigmatic features, or is it just a cosmic coincidence? The more we study them, the more questions arise. Even NASA's Juno spacecraft, which has flown closer to Jupiter than any probe before, has struggled to pin them down. Its infrared instruments reveal tantalizing hints, layers of ammonia and water vapor shifting beneath the spots, but no smoking gun. Hotspots aren't just quirks of Jupiter's atmosphere, they're a direct challenge to our understanding of how planetary weather systems operate. If we can't explain why these dark, silent patches exist on a planet we've studied for centuries, what else might we be missing? Every new observation peels back another layer, revealing just how little we truly know about the king of planets. If there's one thing we know about planets, it's that their magnetic fields are supposed to be symmetrical, neat, orderly bubbles of protection shaped like giant donuts around their equators. But Jupiter, true to form, breaks all the rules. Its magnetic field isn't just strong, it's bizarrely lopsided, bulging outward on one side like a balloon squeezed unevenly. This asymmetry isn't just a quirk, it's a full-blown mystery that's forcing scientists to rethink how planetary magnetic fields are born and sustained. At the heart of the puzzle is Jupiter's dynamo, the churning engine of metallic hydrogen deep inside the planet that generates its magnetic field. On Earth, our dynamo is relatively straightforward, with molten iron swirling around a solid core, creating a magnetic field that's nearly uniform. Jupiter, though, is a different beast. Data from NASA's Juno spacecraft revealed that its magnetic field is shockingly irregular, with a lump of intense magnetism near the equator that scientists nicknamed the Great Blue Spot. Not because it's visible, but because it showed up as a blue-hot anomaly in magnetic field maps. What's causing this imbalance? One leading theory points to Jupiter's rapid rotation. Spinning once every 10 hours, the planet's interior might be churning so violently that the dynamo process becomes unstable, creating pockets of concentrated magnetic energy. Another idea suggests that Jupiter's core, or what's left of it, isn't centered, throwing the entire magnetic field off kilter. Imagine a washing machine with an uneven load wobbling wildly as it spins. Except here, the load is a planetary core, and the wobble distorts the magnetic field on a cosmic scale. The implications are profound. If Jupiter's dynamo doesn't behave like textbook models predict, it could mean we've oversimplified how magnetic fields work in gas giants, or even in exoplanets light years away. Even stranger, the asymmetry isn't static. Juno's observations show the great blue spot drifting slowly westward, as if tugged by invisible currents deeper inside the planet. Could Jupiter's magnetic field be slowly unraveling, or is this just part of a cycle we don't yet understand? Then there's the wild card, Jupiter's moons. Io, Europa, and Ganymede don't just orbit the planet, they're swimming in its magnetosphere, possibly influencing the field in ways we're only beginning to grasp. Some researchers speculate that tidal forces from these moons might be twisting the magnetic field like taffy, adding to the lopsidedness. Others argue the answer lies in Jupiter's atmosphere itself, where jet streams deeper than Earth's diameter might be dragging the magnetic field out of alignment. One thing's certain, Jupiter's wonky magnetic field isn't just a curiosity, it's a clue. By studying its irregularities, scientists are piecing together a new understanding of how planetary dynamos operate under extreme conditions. And with every orbit Juno completes, we're peeling back another layer of this magnetic enigma, revealing just how much we still have to learn about the hidden forces shaping our solar system's largest planet. When you picture planetary rings, Saturn's dazzling icy hoops likely come to mind, but Jupiter has its own set, though they're so faint they weren't even discovered until 1979, when Voyager 1 zipped past and spotted them by sheer chance. Unlike Saturn's bright, icy rings, Jupiter's are wispy and dark, made mostly of dust so fine it's more like smoke than solid material. How does a planet with no obvious ring-building process end up with these ghostly halos? The answer might lie in violent, catastrophic collisions between Jupiter's own moons, scattering debris into space and painting the planet with these ethereal rings. Jupiter's rings are divided into 4 main sections, each with its own quirks. The brightest, known as the main ring, stretches from about 70,000 to 140,000 miles above Jupiter's cloud tops, but bright is relative. It's still 1,000,000 times fainter than Saturn's iconic rings. Beyond it lies the halo ring, a puffier, more diffuse band shaped like a donut, followed by 2 gossamer rings named after the moons that likely birthed them, Amalthea and Thebe. These outer rings are so thin they're practically translucent, fading into nothingness as they stretch millions of miles into space. What's truly bizarre is where this dust comes from. Saturn's rings are mostly ice, chipped off comets or shattered moons over billions of years. Jupiter's rings, though, are made of rocky material, darker than asphalt and just as mysterious. Scientists think micrometeorites constantly pelt Jupiter's inner moons, like tiny jackhammers blasting dust off their surfaces. The planet's immense gravity then corrals that debris into orbit, sculpting it into those faint rings. But there's a twist. Some of this dust might not come from gentle erosion. Ancient moon-shattering impacts could have thrown massive amounts of material into space, creating temporary rings that faded over time, leaving only the faint traces we see today. The biggest clue lies with Jupiter's smallest moons. Amalthea and Thebe, 2 of the planet's tiniest satellites, orbit right inside the gossamer rings, and their gravitational pulls seem to shape the rings' edges. Even stranger, these moons are redder than Mars, stained by sulfur from Io's volcanic eruptions, which might explain why the rings are so dark. If dust from these moons is continually replenishing the rings, it would carry that same reddish tint, making them nearly invisible against the blackness of space. But why don't these rings disappear? On Saturn, icy rings can linger for eons, but Jupiter's dusty rings should spiral inward and vanish within decades, pulled down by the planet's gravity. The fact that they're still here suggests an ongoing supply, like a cosmic conveyor belt, where new dust constantly replaces what's lost. Some researchers even speculate that Jupiter's rings might pulse in brightness, flaring up briefly after major impacts before fading back into obscurity. The deeper mystery is whether we're seeing a temporary feature or something more enduring. If Jupiter's rings are born from destruction, could they vanish entirely one day? Or are they a permanent fixture, quietly sustained by unseen moonlets and microcollisions? One thing's certain, these ghostly rings are a stark reminder that even the faintest features in our solar system can hold the wildest stories. And as long as Jupiter's moons keep dancing in the planet's shadow, those whispers of dust will keep spinning their silent, enigmatic tale. At Jupiter's poles, the weather doesn't just defy expectations, it feels like something out of a cosmic art gallery. When NASA Juno spacecraft first captured close-up images of the planet's north and south poles, scientists were stunned. Instead of the expected chaos of storms colliding and merging, they found something eerily precise: geometric clusters of cyclones arranged like petals on a flower. At the North Pole, 8 storms spiral around a central cyclone, while the South Pole hosts 5, each one wider than the continental United States, yet locked in a perfect, unchanging dance. What makes these polar cyclones so baffling isn't just their symmetry, it's their stubborn refusal to merge. On Earth, when hurricanes get too close, they either repel each other or combine into a single, larger storm. But Jupiter's polar cyclones have been circling the same spots for years, their edges nearly touching yet never collapsing into one another. Some researchers compare them to gears in a machine, each storm's outer winds pushing against its neighbors just enough to maintain balance. Others think the cyclones might be rooted deep in Jupiter's atmosphere, like spinning tops anchored to an invisible floor, preventing them from drifting too close. The real mystery lies in the energy source. Storms this massive should require colossal amounts of power to sustain themselves, yet Jupiter's poles receive less sunlight than anywhere else on the planet. One theory suggests these cyclones act like chimneys, funneling heat from Jupiter's scorching interior up through the atmosphere. Another wild idea proposes that the storms are self-sustaining, their own winds generating enough turbulence to keep them spinning indefinitely, like a perpetual motion machine on a planetary scale. Then there's the enigma of their shapes. The North Pole's octagon and the South Pole's pentagon are so precise they almost look engineered. Could there be some underlying fluid dynamics at play, a natural pattern emerging from the planet's rotation and magnetic field? Or is this a phenomenon we've never seen anywhere else in the universe? Juno's data adds another layer to the puzzle. The spacecraft's microwave readings revealed that these cyclones extend deep, perhaps hundreds of miles below the cloud tops, suggesting they're not just surface features but towering structures with roots in Jupiter's hidden layers. Even more curiously, the central cyclones at both poles spin in the opposite direction of the surrounding storms, creating a whirlpool-like effect that defies conventional weather models. Some scientists speculate that Jupiter's powerful magnetic field might be shaping these storms, acting like an invisible hand guiding their positions. Others point to the Coriolis effect, the same force that shapes Earth's hurricanes but amplified by Jupiter's rapid spin into something far more complex. And then there's the lingering question: are these clusters permanent, or will they eventually destabilize? If they've lasted since Juno's arrival in 2016, could they have been there for centuries, unnoticed until now? Every new flyby peels back another layer of the mystery. These cyclones aren't just storms, they're a masterclass in atmospheric physics, challenging everything we thought we knew about how weather works on gas giants. And as long as they keep spinning, they'll remain one of Jupiter's most mesmerizing riddles, a reminder that even the most familiar planets can still surprise us. Jupiter might be a gas giant, but one of its most perplexing secrets revolves around something far more familiar: water. For decades, scientists have tried to measure just how much water is hidden beneath the planet's turbulent clouds, and the results have been anything but consistent. Some probes, like Galileo's atmospheric entry in 1995, suggested Jupiter was surprisingly dry, with water levels far lower than expected. Other measurements, like those from the Juno spacecraft, hint at pockets where water might be 10 times more abundant. This discrepancy isn't just a scientific hiccup, it's a mystery that could rewrite the story of how Jupiter and our entire solar system came to be. The debate centers on two competing theories about Jupiter's formation: the dry and wet planet scenarios. If Jupiter formed close to the Sun, where temperatures were too high for water ice to exist in the early solar system, it should have started as a relatively dry world, later capturing moisture from comets and icy debris. But if it formed farther out, where water ice was plentiful, it should have been born wet, with water molecules baked into its very structure. The problem: our measurements can't seem to agree on which scenario is correct. The Galileo probe's findings were the first shock. As it plunged into Jupiter's atmosphere, it detected only a trace amount of water, about 1/10 the expected concentration. Scientists initially chalked it up to bad luck, assuming the probe had descended through an unusually dry patch, like landing in a desert on Earth. But then Juno arrived, armed with microwave sensors capable of peering deeper into Jupiter's atmosphere. Its data revealed swirling pockets where water appeared far more abundant, suggesting the planet's moisture might be distributed in uneven, storm-driven layers, like a cosmic sponge with dry and soaked regions. Complicating matters further is Jupiter's Great Red Spot. Recent studies using Earth-based telescopes found startling evidence that the storm might contain towering plumes of water-rich air, rising from depths where temperatures and pressures turn hydrogen and oxygen into a supercritical fluid, a state where water acts more like a gas and liquid simultaneously. Could this explain the inconsistency? If water is trapped beneath thick cloud decks well hidden from most probes, it might only surge upward in certain storms, creating fleeting windows where moisture becomes detectable. The stakes are higher than they seem. Water isn't just a curiosity, it's a time capsule. The amount of water in Jupiter's atmosphere holds clues about the primordial soup of gas and dust that birthed the solar system. If Jupiter is wetter than we thought, it might mean the building blocks of planets were more hydrated than models predict, reshaping our understanding of how worlds form. Alternatively, if the dryness holds, it could imply Jupiter migrated inward from its birthplace, scattering icy debris in its wake, a cosmic bulldozer that reshaped the early solar system's architecture. For now, the mystery remains unsolved. Upcoming missions, like the European Space Agency's JUICE probe, aim to tackle the question head-on, mapping water distribution across Jupiter's atmosphere with unprecedented precision. Until then, scientists are left piecing together fragments of data, debating whether the planet's true nature is dry, wet, or something far more unpredictable. One thing's certain: Jupiter's water puzzle isn't just about weather. It's about the very origins of our cosmic neighborhood, and with every new observation, we're one step closer to understanding the story written in those hidden, swirling clouds. Jupiter's lightning should feel familiar after all. It's the same basic physics as Earth's thunderstorms, right? Not even close on our planet. Lightning crackles with radio noise, a telltale signature that helped scientists detect it from space. But when the Voyager probe first listened to Jupiter's storms in 1979, it heard something eerie, flashes of light with no radio static at all. These weren't just silent storms, they were breaking every rule we thought we knew about how lightning behaves. the strangeness doesn't stop there. On Earth, lightning thrives where warm, moist air rises. Think tropical thunderstorms or summer afternoons. Jupiter, though, flips the script. Here, the most intense bolts erupt near the poles and in the cold, dry bands of the planet's atmosphere, far from the warmer equatorial zones where you'd expect instability. Some of these discharges are monsters, packing 1,000 times the energy of an average earthly bolt, enough to briefly outshine the sun in ultraviolet light. Yet they flicker silently, like cosmic Morse code we're only beginning to decipher. So what's fueling these enigmatic strikes? One clue lies in their structure. Earth's lightning races between oppositely charged regions of clouds or between clouds and the ground. Jupiter's lightning might be jumping between layers of ammonia and water clouds, separated by vast distances in the planet's deep atmosphere. Without solid ground to anchor the charges, the bolts could be stretching dozens of miles vertically, their energy dissipating in ways that suppress radio waves. Another theory points to Jupiter's exotic chemistry, ammonia acting as an antifreeze, mingling with water vapor to create slushy, electrically conductive clouds unlike anything in our skies. Then there's the wild card, Jupiter's immense pressure. At the depths where these bolts form, the air isn't just dense, it's a supercritical fluid blurring the line between gas and liquid. Lightning in this environment might behave more like an explosion than a jagged bolt, a sustained energy release that looks nothing like the instantaneous flashes we see on Earth. Some researchers even speculate these discharges could be shallow lightning, igniting in ammonia-rich clouds higher up than traditional models predict, where frigid temperatures create exotic forms of hail. The biggest puzzle remains the radio silence. One leading idea suggests Jupiter's lightning emits at frequencies too low for most instruments to detect, a basso profundo rumble lost in the noise of the planet's own magnetic field. Or perhaps the bolts are fundamentally different, less of a sudden zap and more of a rolling energy wave, spreading through the atmosphere like a slow-motion spark. Every new observation adds layers to the mystery. Juno's recent discoveries of mushball, hail, slushy, ammonia-infused ice chunks might explain how charge builds up in regions previously thought too cold for storms. Meanwhile, Hubble's snapshots of superbolts near Jupiter's poles hint at a global weather system far more complex than our own, where energy circulates in ways we're only beginning to map. One thing's clear, Jupiter's lightning isn't just a scaled-up version of Earth's. It's a phenomenon rewriting the textbooks on atmospheric electricity, proving that even the most familiar forces can take alien forms when unleashed on a cosmic scale. And with every bolt that flares in Jupiter's clouds, we're reminded just how much we still have to learn about the hidden fires of our solar system's largest planet. Jupiter's interior is one of the greatest unsolved puzzles in our solar system, a place where the very rules of planetary formation seem to bend. For years, scientists pictured Jupiter with a textbook-perfect core, a dense, compact ball of rock and metal at its center, like the pit inside a peach. But when NASA's Juno spacecraft began mapping the planet's gravity field, it revealed something far more bizarre, a core that isn't solid at all, but a fuzzy, diluted mess of heavy elements bleeding into the surrounding hydrogen soup. This discovery didn't just tweak our models, it shattered them, forcing astronomers to reconsider how gas giants are born. The traditional story goes like this: planets form from a swirling disk of dust and gas around a young star. Tiny grains clump together, building larger and larger bodies until one grows massive enough, about 10 Earth masses, to start hoovering up vast amounts of gas from the disk. This collapsing gas forms the thick atmosphere of a gas giant, while the original clump becomes its solid core. It's a clean, logical process, except Jupiter's hazy core throws a wrench into the entire narrative. If the core isn't a distinct, dense sphere, how did Jupiter ever gather enough gravity to attract all that gas in the first place? One radical explanation suggests Jupiter's core might have been eroded over billions of years, dissolved by the extreme pressures and temperatures at the planet's heart. Picture dropping a sugar cube into scorching tea. The edges blur, then melt away entirely. On a planetary scale, this could mean Jupiter's once solid core was gradually chewed up by swirling currents of metallic hydrogen, leaving behind only a diffuse smudge of heavier elements. But there's a problem with this idea. The timescales don't quite add up. Models show erosion would take far longer than Jupiter's age to fully dismantle a core. That's led to an even wilder theory. What if Jupiter never had a traditional core to begin with? Some scientists now propose the planet formed through a process called pebble accretion, where tiny grains of dust and ice clumped together directly into a loose, fluffy aggregate, never compressing into a solid heart. Imagine building a snowman not by rolling tight snowballs, but by piling up handfuls of powdery flakes. In this scenario, Jupiter's core was always more of a suggestion than a concrete object. Its heavy elements spread unevenly through the inner layers like chocolate chips in a half-mixed batter. The implications ripple far beyond Jupiter. If gas giants can form without distinct cores, it challenges our assumptions about exoplanets, especially the hot Jupiters orbiting close to their stars. Could their cores be fuzzy too? Even closer to home, Saturn's interior models might need revisiting, as its gravity field shows similar oddities. The mystery deepens when you consider Jupiter's lopsided magnetic field, which Juno found was stronger in one hemisphere, a quirk that might trace back to this uneven, dissolving core. Perhaps the most tantalizing clue lies in Jupiter's moons. The Galilean satellites Io, Europa, Ganymede, and Callisto are essentially planetary bodies themselves, rich in rock and metal. Some researchers speculate these moons might be fragments of Jupiter's original core, blasted outward by ancient collisions. If true, it would mean the planet's heart wasn't just eroded but violently scattered, leaving behind a ghostly imprint in its gravity field. Every new orbit of Juno peels back another layer of this enigma. The spacecraft's latest gravity maps show hints of a denser region deep inside, wrapped in layers of exotic materials. Perhaps the last remnants of that long-lost core, or something even stranger. What's clear is that Jupiter's interior isn't just a scientific curiosity, it's a cosmic crime scene, with clues that could rewrite the story of how planets take shape. And as long as that fuzzy core keeps defying explanation, it remains one of the solar system's most profound puzzles. Jupiter's atmosphere isn't just turbulent, it's a swirling, three-dimensional labyrinth of gases, each layer behaving like a rogue painter splashing colors across an ever-changing canvas. From afar, those iconic stripes, alternating bands of white, red, and brown, seem almost orderly, but zoom in and chaos reigns. Unlike Earth's relatively stable weather systems, Jupiter's cloud layers operate on a scale that defies prediction, with storms materializing, merging, or vanishing within days, leaving scientists scrambling to decode the rules of this alien meteorology. At the heart of this chaos is chemistry. Jupiter's stripes are sculpted by competing jet streams, some racing eastward, others westward at speeds up to 400 miles per hour, faster than a Category 5 hurricane. These winds carve the planet into distinct zones and belts, but what gives each its color remains hotly debated. The lighter zones, where gas rises, are rich in ammonia ice, reflecting sunlight like frosted glass. The darker belts, where air sinks, may harbor compounds like ammonium hydrosulfide or even complex organic molecules, their exact recipes still unknown. Then there's the wild card, phosphorus. Recent studies suggest traces of this element, possibly dredged from deep within Jupiter, could react with sunlight to create the planet's signature scarlet hues, especially in the Great Red Spot. Yet chemistry alone can't explain the turbulence. Earth's weather is driven largely by solar heat and surface friction, but Jupiter, 5 times farther from the Sun, has no solid surface to disrupt its winds. Instead, the planet's own internal heat left over from its violent formation fuels the chaos. This energy surges upward, colliding with the frigid outer atmosphere to create storms that dwarf our entire planet. Some researchers compare it to a boiling pot, where heat from the stove Jupiter's core bubbles through the water its atmosphere. Only here, the water is a toxic brew of hydrogen, helium, and ammonia, swirling under pressures that crush metal like tin foil. The real enigma lies in the layers themselves. Data from Juno's microwave radiometer revealed that Jupiter's infamous belts and zones aren't just surface decorations, they plunge hundreds of miles down, with roots deep enough to engulf Earth's tallest mountains. Even stranger, these structures seem to shift over time. Historical records show some bands darkening or fading over decades, while others sprout sudden outbreaks of storms, like the explosive string of pearls that appeared in Jupiter's southern hemisphere in 2016, a chain of white ovals stretching 30,000 miles, each a storm in its own right. Then there's the ammonia mystery. Juno found towering plumes of this gas erupting near the equator, far from where models predicted it should be. Some scientists think these plumes are evidence of colossal weather systems, akin to Earth's Hadley cells but operating on a planetary scale, funneling ammonia from the depths to the cloud tops. Others propose the ammonia is being hidden at mid-latitudes, absorbed by unknown chemicals, or even forming slushy ammonia water hailstones that rain back into the abyss. What makes Jupiter's atmosphere truly unruly, though, is its refusal to follow any script. Earth's jet streams are famously fickle, but Jupiter's take unpredictability to extremes. In 2019, astronomers watched in disbelief as a chunk of the planet's southern equatorial belt, a dark ribbon that had persisted for centuries, suddenly shredded like tissue paper, its fragments spiraling into chaotic eddies before reforming months later. No existing model saw it coming. The deeper we probe, the clearer it becomes. Jupiter's clouds aren't just weather. They're a dynamic, evolving lab for physics we've barely begun to grasp, where familiar forces play out on scales so vast they become unrecognizable. Every storm, every band, every chemical reaction is a piece of a puzzle. We're still assembling one that might hold the key to understanding not just Jupiter, but the turbulent births of gas giants across the cosmos. High above Jupiter's churning storms, where the planet's colorful clouds thin into hazy stillness, lies a layer of the atmosphere that shouldn't exist, a frigid zone scientists call the stratosphere. Normally, a planet's stratosphere gets warmer with altitude, heated by sunlight absorbing into gases like ozone. But Jupiter's upper atmosphere defies logic, plunging into temperatures as low as -200 degrees Fahrenheit, colder than some regions of Pluto. This cold trap has left researchers scratching their heads because, according to every standard model of planetary atmospheres, Jupiter's stratosphere should be toasty, not freezing. The mystery deepens when you consider the energy pouring into this region. Sunlight bathes Jupiter's upper atmosphere, and the planet's own internal heat surges upward from below. Combine that with constant bombardment from charged particles trapped in Jupiter's magnetic field, and you'd expect a furnace, not an icebox. So why is it so cold? One leading theory points to invisible atmospheric waves, ripples of pressure and temperature that propagate through the gas giant's air like sound waves through water. These waves, generated by storms far below, might be carrying energy away from the stratosphere, effectively acting like a cosmic air conditioner. Imagine tossing a pebble into a pond. The ripples spread outward, stealing energy from the point of impact. On Jupiter, something similar could be happening vertically. Turbulence from the planet's monstrous storms might launch waves that travel upward, expanding and cooling as they rise. By the time these waves reach the stratosphere, they could be dissipating their energy into space, leaving behind a layer of chilled gas. It's a delicate balancing act, one that requires just the right mix of wave frequency and atmospheric density to create this unexpected cold zone. But waves alone might not tell the whole story. Another clue comes from Jupiter's auroras. These dazzling light shows aren't just pretty, they're pumping energy into the poles, yet the stratosphere remains stubbornly cold elsewhere. That suggests the cooling isn't uniform but patchy, as if hidden currents are redistributing heat in ways we can't yet map. Some researchers speculate that exotic chemicals in Jupiter's upper atmosphere, like hydrocarbons or complex organic molecules, might be acting as thermal shields, absorbing certain wavelengths of sunlight while letting others escape. On Earth, greenhouse gases trap heat, but on Jupiter, the opposite could be happening, with certain compounds radiating more energy than they retain. The implications stretch beyond Jupiter. If wave-driven cooling or unseen chemistry can override expected heating patterns, it could mean we've misunderstood how gas giants age. Hot Jupiters orbiting close to their stars, for instance, might harbor similar cold layers, challenging assumptions about their atmospheres. Even our own solar system's ice giants, Uranus and Neptune, have oddly chilly upper atmospheres. Could the same physics be at work? Juno's recent observations add another twist. The spacecraft detected eerie hotspots in Jupiter's stratosphere, localized regions where temperatures spike unexpectedly, like tiny bonfires in a frozen wasteland. These anomalies don't align with known storms or auroras, leaving scientists to wonder if Jupiter's atmosphere is playing a game of thermodynamic chess with rules we're only starting to guess. For now, the stratosphere remains one of Jupiter's quietest enigmas, a layer of the planet that refuses to follow the script. And until we can send probes that linger in this elusive zone rather than briefly skimming past, its secrets will stay locked in that deep, unexpected cold. Jupiter's moon system looks like a cosmic nursery with a peculiar gap, dozens of tiny moons, 4 massive Galilean satellites, and almost nothing in between. It's as if nature skipped a size category entirely, leaving scientists to wonder, where are all the mid-sized moons? This isn't just a curiosity, it's a clue to the violent history hidden in Jupiter's gravitational grip. Start with the numbers. Jupiter boasts at least 92 moons, but most are tiny, irregularly shaped rocks less than 6 miles across, captured asteroids, likely snagged during the solar system's chaotic youth. Then there's the Big Four: Io, Europa, Ganymede, and Callisto, each thousands of miles in diameter, large enough to be planets in their own right, but between these extremes, almost nothing. Only a handful of moons like Amalthea and Himalaya barely crack the 50-mile mark, a mere rounding error compared to the Galilean giants. This bizarre size distribution defies probability. In most natural systems, you'd expect a smooth gradient, plenty of small objects, fewer medium ones, and a handful of large ones. Jupiter's moons, though, are missing an entire chapter. So what happened to the middle class? One compelling theory points to Jupiter's ferocious gravity. Early in the solar system's history, the planet's pull would have been a wrecking ball, shredding any mid-sized moons that dared form too close. Collisions would have been catastrophic. Imagine 2 Mars-sized bodies slamming together at thousands of miles per hour, fracturing into debris that either spiraled into Jupiter or coalesced into smaller survivors. The 4 Galilean moons might be the exception simply because they formed farther out, where the chaos was slightly less intense, but there's a twist. Some researchers argue the missing mid-sized moons weren't destroyed, they were absorbed. Jupiter's largest moons, particularly Ganymede and Callisto, show signs of ancient globe-shaking impacts. Craters the size of continents hint at collisions so violent they could have vaporized rival moons, their material swallowed whole by the victors. In this scenario, the Galilean moons didn't just avoid destruction, they grew fat on the remains of their competitors, leaving behind a graveyard of lost mid-sized worlds. Another clue lies in the orbits. Smaller, irregular moons tend to follow wild, elliptical paths, often circling backward compared to Jupiter's rotation. The Galilean moons, by contrast, orbit in neat, near-circular planes. This stark divide suggests two separate origins, the tiny moons captured later, the Big Four born alongside Jupiter itself. Medium moons, if they ever existed, might have been caught in the crossfire, torn apart by shifting gravitational tides as Jupiter's system settled into its current arrangement. Perhaps the most haunting possibility is that intermediate moons never formed at all. Jupiter's birth was so turbulent, its protoplanetary disk so thick with collisions, that mid-sized objects simply couldn't stabilize. The planet's gravity would have kept the debris field in constant upheaval, like a blender set to cosmic speed, preventing anything between dust and dwarf planets from taking shape. Whatever the answer, this gap in moon sizes isn't just a quirk. It's a window into the brutality of the early solar system. Every missing mid-sized moon is a silent witness to the forces that shaped not just Jupiter, but every planet in our neighborhood. And until we send landers to dig into the icy crusts of Europa or Ganymede, searching for fragments of those lost worlds, their absence will remain one of Jupiter's quietest, most persistent mysteries. Jupiter's moon Io is the solar system's most volcanic world, a place where eruptions are so frequent and violent they've been caught spewing lava hundreds of miles into space. But Io's fire isn't just a local spectacle. It's reshaping Jupiter itself, pumping the planet's magnetosphere with enough material to create some of the weirdest phenomena ever observed. Every second, Io blasts nearly 2,000 pounds of sulfur dioxide gas into the void, a volcanic exhaust fan on a cosmic scale. Jupiter's gravity then rips this material away, sculpting it into a donut-shaped cloud of superheated plasma that orbits the planet like a glowing halo. Scientists call this the Io plasma torus, and it's anything but peaceful. The torus is a maelstrom of charged particles, so energetic it glows in ultraviolet light, a ring of fire visible from Earth-based telescopes. But the real magic happens when Jupiter's magnetic field grabs hold of this plasma. Like a cosmic slingshot, the planet's rotation accelerates these particles to nearly light speed, creating electrical currents so powerful they could power human civilization 1,000,000 times over. Some of this energy erupts as radio waves, beaming into space like an alien broadcast. These signals, known as Jovian radio emissions, pulse with eerie regularity, earning nicknames like Jupiter's heartbeat for their rhythmic, almost musical quality. What makes Io's influence truly bizarre, though, is how it warps Jupiter's magnetosphere. Normally, a planet's magnetic field is symmetrical, like a bubble around a child's wand. But Io's constant volcanic fallout forces Jupiter's field into a lopsided shape, stretching it like taffy on the side where the moon orbits. This distortion creates flux tubes, invisible pipelines of electricity linking Io directly to Jupiter's poles. When these tubes snap, they unleash million-amp discharges that ignite auroras brighter than entire cities, visible even when Io itself is shrouded in shadow. The most stunning evidence of this connection came in 2007, when NASA's New Horizons spacecraft caught Jupiter's auroras flaring precisely where Io's flux tubes touched down. The timing was no coincidence, it was proof of a real-time celestial circuit, with Io as the spark plug. But the moon isn't just injecting energy, it's also stealing it. As Io plows through Jupiter's magnetic field, it generates friction strong enough to heat the moon's interior, keeping its volcanoes hyperactive in a self-sustaining loop. Jupiter squeezes Io, Io feeds Jupiter, and the cycle continues, a gravitational tango with consequences visible across the solar system. Yet for all we've uncovered, mysteries remain. Why do Io's volcanic plumes sometimes trigger radio bursts while others pass silently? How does the plasma torus maintain its structure instead of dispersing into space? And could similar dynamics be at play on exoplanets with volcanic moons? Each eruption on Io is a fresh experiment, a chance to witness physics that doesn't exist anywhere else in our neighborhood. As long as lava flows on this tiny moon, Jupiter will keep answering with celestial fireworks, a reminder that even the quietest orbits can spark cosmic chaos. Jupiter spins faster than any other planet in our solar system, completing a full rotation in just under 10 hours. But here's the twist: not all parts of the planet spin together. Deep below those churning clouds, Jupiter's layers might be rotating at different speeds, like a celestial onion with each shell turning independently. This bizarre behavior isn't just a curiosity. It could hold the key to some of the planet's most puzzling features, from its lopsided magnetic field to the turbulent storms that rage across its surface. The first clues came from Jupiter's gravity field. When NASA Juno spacecraft mapped the planet's internal structure, scientists expected to find uniform rotation, a rigid body spinning as one. Instead, the data revealed subtle distortions, hinting that the outer atmosphere might be lagging behind the deeper layers by a fraction of a second per rotation. That tiny difference adds up over thousands of miles, creating shear forces powerful enough to warp the planet's magnetic field and stir its storms into frenzy. Imagine a blender where the bottom spins faster than the top. The chaos inside Jupiter could be just as extreme, with layers of hydrogen and helium grinding against each other like cosmic gears. What's driving this differential rotation? The answer might lie in Jupiter's interior pressures. At certain depths, hydrogen gas gets squeezed so intensely it transitions into a bizarre metallic state, a fluid that conducts electricity like metal but flows like liquid. This metallic hydrogen layer is thought to power Jupiter's dynamo, generating its colossal magnetic field. But if the outer gaseous envelope rotates slightly slower than this metallic core, it could twist the magnetic field lines, explaining why Jupiter's magnetosphere is so asymmetrical. Some researchers compare it to a car engine with misaligned belts still running, but with vibrations that warp the entire system. The implications are staggering. If Jupiter's interior is truly a series of nested, rotating shells, it challenges our basic understanding of how gas giants evolve. Planetary models typically assume these worlds rotate uniformly after formation, but Jupiter's behavior suggests its layers might have never fully synchronized. Alternatively, the planet's rapid spin and lack of a solid surface could allow each layer to find its own rhythm, like dancers in a cosmic ballet responding to different tempos. Even more intriguing are the storms, Jupiter's jet streams. Those alternating bands of eastward and westward winds might be surface manifestations of these deeper rotations. If the inner layers tug on the outer atmosphere at varying speeds, they could create the planet's iconic stripes with turbulent boundaries where the winds clash. The Great Red Spot itself might owe its longevity to these underlying currents, drawing energy from the mismatch between layers like a whirlpool fed by hidden underwater springs. Yet mysteries remain. Juno's gravity measurements only scratch the surface, literally. The spacecraft can't peer deep enough to map the exact boundaries between these rotating layers, leaving scientists to speculate about where one ends and the next begins. Some theories suggest the transition happens gradually, with rotation speeds shifting smoothly over hundreds of miles. Others propose sharp divides, invisible boundaries where Jupiter's interior suddenly changes pace, like gears clicking into new positions. One thing's certain: Jupiter's odd rotation isn't just a quirk. It's a window into the hidden mechanics of gas giants. If we can unravel how its layers interact, we might finally understand why its storms endure, why its magnetic field warps, and even how similar worlds across the galaxy behave. Until then, this multi-speed giant keeps spinning its secrets just out of reach, a cosmic puzzle wrapped in swirling clouds and buried deep beneath the surface. Deep within Jupiter's swirling magnetic chaos, something invisible to the human eye pulses like a cosmic lighthouse, X-ray auroras, blasting out flares so intense they momentarily outshine the entire planet. Unlike Earth's shimmering green auroras, these high-energy bursts are born from a process so alien, scientists still aren't entirely sure how they work. The most baffling part, they flicker with eerie precision, flaring every 27 minutes like clockwork, as if Jupiter itself has a heartbeat. What makes these X-rays so puzzling is their source. On Earth, auroras ignite when solar wind particles collide with our magnetic field, but Jupiter's X-ray flares don't sync neatly with solar activity. Instead, they seem tied to the planet's own magnetic vibrations, ripples coursing through its field like plucked guitar strings. One leading theory suggests charged particles, possibly from volcanic Io, get trapped in Jupiter's magnetic grip, then surf these vibrations down to the poles at nearly light speed. When they slam into the atmosphere, the impact unleashes X-rays powerful enough to be spotted by telescopes light years away. But here's where it gets weirder. Recent data from NASA Chandra X-ray Observatory revealed these auroras sometimes split into two distinct pulses, one at the North Pole, one at the South, dancing out of sync by mere minutes. It's as if Jupiter's magnetic field is a tuning fork struck twice, ringing at slightly different frequencies. Some researchers think this hints at hidden asymmetries in the planet's core, where lopsided magnetic fields vibrate independently. Others propose the answer lies in Jupiter's magnetotail, a stretched-out wake of magnetism trailing behind the planet like a comet's tail. When solar wind tugs on this tail, it might snap back like a rubber band, sending shockwaves rippling toward the poles and triggering those eerie X-ray beats. Then there's the wild card, Jupiter's moons. Europa and Ganymede, both icy worlds, plow through the planet's magnetic field, potentially stirring up plasma waves that amplify the auroras. Imagine dragging a spoon through honey. The thicker the resistance, the more energy gets trapped. If these moons are stirring Jupiter's magnetic soup, they could be indirectly fueling the X-ray machine. Yet even this doesn't fully explain the regularity of the pulses. Why 27 minutes? Why not 10 or 50? The precision suggests some underlying rhythm, a fundamental physics we haven't yet grasped. What's clear is that Jupiter's X-ray auroras aren't just scaled-up versions of Earth's, they're a phenomenon unlike anything else in our solar system. And every flicker holds clues, not just about Jupiter's hidden workings, but about how magnetic fields shape worlds across the cosmos. Until we land a probe in those turbulent polar regions, these pulsing lights will remain one of the planet's most electrifying mysteries. When we think of lightning, we picture brilliant forks of electricity splitting the sky, but Jupiter has a far stranger trick up its sleeve. Hidden within its storm clouds are bursts of dark lightning, invisible to our eyes yet packing enough energy to dwarf Earth's most powerful storms. These eerie discharges were first detected not by their light, but by the gamma rays they emit, a telltale signature of electrons accelerating to nearly the speed of light. It's a phenomenon so alien, scientists initially doubted their instruments. The discovery came from NASA's Fermi Gamma Ray Space Telescope, which in 2012 caught flashes of gamma radiation emanating from Jupiter's cloud tops. Unlike normal lightning, which lights up the sky with visible photons, dark lightning unleashes its energy in the form of high-energy electrons colliding with atmospheric molecules. The result, invisible bursts of radiation so intense they briefly outshine the planet's own auroras. Imagine a thunderstorm where the flashes are entirely black, detectable only by the atomic-level fireworks they spark. What makes these events even more baffling is where they occur. On Earth, lightning thrives in regions of rising warm, moist air, but Jupiter's dark lightning seems to prefer the frigid, ammonia-rich layers high above its water clouds. Some researchers speculate that the planet's unique chemistry plays a role. At those altitudes, ammonia acts as an antifreeze, mingling with water vapor to create slushy, electrically charged clouds unlike anything in our skies. When these exotic clouds discharge, they might generate particle beams rather than traditional bolts, like a natural particle accelerator hidden in the clouds. Even stranger, these gamma-ray flashes appear to pulse in sync with Jupiter's rotation, flaring most intensely when certain storm systems face Earth. That rhythmic pattern hints at a global electrical circuit, where Jupiter's magnetic field channels energy between its poles and equator like a cosmic battery. Some theories suggest the planet's own rapid spin twists magnetic field lines until they snap, launching electrons into the atmosphere like bullets from a railgun. The implications stretch far beyond Jupiter. If dark lightning is common on gas giants, it could explain mysterious gamma-ray signals from distant exoplanets, hints of invisible storms raging in alien atmospheres. Closer to home, it forces us to rethink the very definition of lightning. Is it still lightning if no light is emitted, or is this something entirely new, a high-energy shadow dance we're only beginning to decode? One thing's certain: Jupiter's dark lightning isn't just a curiosity. It's a window into the untamed physics of gas giants, where the rules of electricity rewrite themselves in ways we're only starting to grasp. And with every flicker of gamma rays, this hidden storm world reminds us how much we still have to learn about the invisible forces shaping our solar system. Jupiter's equator should be a hotbed of ammonia at least. That's what every atmospheric model predicted. When NASA Juno spacecraft arrived in 2016, scientists expected to find this key ingredient evenly distributed, rising in thick plumes from the planet's depths and condensing into visible clouds. Instead, Juno's microwave radiometer revealed something startling: a vast ammonia pore belt stretching around Jupiter's midsection, as if someone had scrubbed the chemical clean from the atmosphere. This wasn't just a minor discrepancy, it was a direct challenge to our understanding of how gas giants circulate their atmospheres, and it hinted at hidden currents operating far deeper than we can see. The mystery begins with Jupiter's sheer scale. Unlike Earth, where weather is confined to a thin shell near the surface, Jupiter's atmosphere plunges thousands of miles downward, transitioning from familiar gases into exotic states like metallic hydrogen. Ammonia, a compound of nitrogen and hydrogen, should be abundant throughout these layers, acting as a tracer for atmospheric motion. Yet at the equator, Juno found ammonia levels dropping sharply, not just at the cloud tops but hundreds of miles below, in regions where the gas ought to be well mixed. It's like expecting a stirred cup of coffee to have even creaminess, only to dip a spoon in and find the bottom half mysteriously black. So where did the ammonia go? One leading theory suggests it's being sucked downward by colossal atmospheric downdrafts akin to cosmic sinkholes. On Earth, descending air tends to be dry. Think of deserts at 30 degrees latitude where high-pressure systems push moisture away. Jupiter's equatorial belt might operate similarly, with dry gas plunging so fast it drags ammonia deep below the reach of Juno's sensors. If true, this would imply a previously unknown ammonia conveyor belt, where the gas cycles between the upper and lower atmosphere over decades or centuries. But there's a twist. Juno also spotted sporadic ammonia-rich plumes erupting near the equator, towering geysers of gas that punch through the depleted zone like fountains. These plumes suggest the ammonia isn't gone permanently, but temporarily sequestered, trapped in a layer beneath the visible clouds. Some researchers compare it to a planetary-scale game of hide and seek, where ammonia ducks out of sight only to reappear in unpredictable bursts. The wildest possibility, Jupiter's ammonia might be forming exotic compounds we've never accounted for. At the crushing pressures and temperatures found deep in the planet's atmosphere, ammonia could react with other elements to create crystals or slushy mixtures too heavy to rise. Imagine snowfall, but instead of water ice, it's ammonia hydrosulfide flakes drifting silently into the abyss, invisible to our instruments. This isn't just academic curiosity. Ammonia is a cornerstone of Jupiter's weather. It helps form clouds, influences storm formation, and even plays a role in those mysterious dark lightning bursts. If we've misjudged its distribution, we might be missing key pieces of the puzzle that explains everything from the great red spot's longevity to the planet's turbulent jet streams. Juno's findings have forced scientists to rethink atmospheric models entirely. New simulations now propose a three-dimensional circulation pattern where ammonia-rich air rises at mid-latitudes, travels toward the equator aloft, then dives back down in a planet-wide loop. It's a radical departure from the old idea of Jupiter's weather being driven mostly by surface-level winds. The bigger question is what else we might be overlooking. If ammonia can vanish from an entire equatorial belt, what other secrets are hiding beneath Jupiter's clouds? Every new discovery peels back another layer, revealing just how little we truly understand about the forces shaping this gas giant's stormy heart. And until we send probes that can linger in those hidden depths, the missing ammonia will remain one of Jupiter's most tantalizing chemical mysteries. Jupiter's jet streams don't just blow, they scream across the planet at speeds that would make a fighter pilot dizzy, reaching up to 400 miles per hour. These ribbons of wind, wider than Earth itself, carve the planet into those iconic stripes we see from space. But here's the puzzle. On Earth, wind speeds slow down due to friction with mountains, oceans, and even the air itself. Jupiter has no solid surface to disrupt its currents, yet these supersonic jet streams should still lose energy over time, collapsing into chaos like a whirlpool in a draining bathtub. So why don't they? What invisible force keeps these atmospheric rivers locked in place century after century? The answer might lie in Jupiter's interior. Unlike our planet, where weather is driven largely by sunlight hitting the surface, Jupiter's own internal heat, left over from its violent birth, fuels its storms. Energy bubbling up from the depths could act like a cosmic treadmill, continuously pumping momentum into those jet streams. Some researchers compare it to a boiling pot of water, where heat from the stove creates rolling convection currents. On Jupiter, those currents might stretch thousands of miles deep, driving winds faster than any hurricane, but even that doesn't fully explain the precision of these bands. Why don't they merge or meander? Why do they stay so neatly separated, like lanes on a cosmic freeway? One radical theory points to Jupiter's magnetic field. The planet's interior is a churning ocean of metallic hydrogen, a form of matter so compressed it conducts electricity like copper wire. As this metallic fluid moves, it generates Jupiter's colossal magnetic field, which could indirectly shape the winds above. Imagine invisible magnetic guardrails channeling the jet streams, preventing them from straying off course. There's evidence for this. Juno's measurements revealed odd fluctuations in Jupiter's gravity field that align with the jet streams, hinting at a deep connection between the planet's interior and its cloud tops. Then there's the wild card turbulence itself. On Earth, turbulence robs energy from wind systems, causing them to dissipate. But Jupiter's sheer size might turn turbulence into a stabilizing force. Picture two rivers flowing side by side. If they're narrow, they'll mix into chaos, but if they're wide enough, they can maintain distinct paths. Jupiter's jet streams are so vast that their turbulence might reinforce their structure rather than disrupt it, like a self-tightening knot. The most baffling aspect is their longevity. Some models suggest these jet streams might have existed since Jupiter's infancy, frozen in time like atmospheric fossils. If true, they're not just weather, they're living records of the planet's formation, shaped by conditions we can only guess at. Every new storm, every ripple in those bands, is a clue to forces operating far below the clouds, in realms where hydrogen flows like liquid metal and pressure crushes matter into forms we've yet to discover. Until we send probes deep into Jupiter's atmosphere, these supersonic highways will remain one of its most enduring riddles, a reminder that even the fastest winds can't outrun the mysteries of the solar system's largest planet. Jupiter's radiation belts aren't just intense, they're apocalyptic, a swirling maelstrom of charged particles so ferocious they could fry most spacecraft in mere months. This lethal halo, discovered in 1959 by the Pioneer probes, outstrips even Earth's Van Allen belts by a staggering margin, packing enough punch to deliver a radiation dose millions of times deadlier than a fatal human exposure. What makes these belts so extreme, and why do they defy every expectation about how planetary magnetic fields should behave? The sheer violence of Jupiter's radiation stems from two factors: the planet's monstrous magnetism and its captive moon, Io. Jupiter's magnetic field is the strongest in the solar system after the Sun's, a turbulent force that whips charged particles to nearly light speed, but it's Io that supercharges the system. The Moon's relentless volcanic eruptions spew sulfur and oxygen ions into space, where Jupiter's gravity and magnetic field shred them into a soup of high-energy electrons and protons. These particles then spiral along magnetic field lines trapped in a deadly donut around the planet, the radiation belt, where they ricochet like bullets in a cosmic shooting range. Why this process generates such extreme radiation remains a puzzle. Earth's belts are tame by comparison, partly because our planet lacks a volcanic moon seeding them with fresh particles. But even accounting for Io's contribution, Jupiter's belts are orders of magnitude hotter than models predict. Some scientists suspect the planet's rapid rotation plays a role, spinning once every 10 hours. Jupiter's magnetic field acts like a particle accelerator, revving electrons to energies that should be impossible under classical physics. Others point to chaotic magnetic reconnection events, where field lines snap and realign near the planet's equator, launching plasma shockwaves that further energize the trapped particles. The consequences for exploration are stark. NASA Juno spacecraft, the most radiation-hardened probe ever built, still had to adopt a polar orbit to minimize exposure, its electronics shielded inside a titanium vault. Even so, Juno's cameras and sensors degrade with every pass, a reminder of how swiftly Jupiter's radiation erodes human technology. Galileo, an earlier mission, wasn't so lucky. Its tape recorder failed repeatedly, and by the mission's end, half its instruments were crippled. Future missions to Europa or Ganymede will face the same gauntlet, forcing engineers to devise ever more exotic shielding, perhaps even using superconducting materials to deflect rather than absorb particle strikes. The greatest mystery isn't just the belt's intensity, but their structure. Earth's radiation zones form neat concentric rings, but Jupiter's are lopsided and patchy, with hotspots where radiation spikes unpredictably. Juno's data revealed one such zone near the equator, where electrons reach energies so high they briefly mimic cosmic rays. No existing theory fully explains these aberrations, though some researchers speculate they're tied to Jupiter's wonky magnetic field or hidden plasma waves resonating through the belts. Then there's the enigma of the belt's outer edge. Unlike Earth's belts, which fade gradually into space, Jupiter's radiation terminates abruptly about 2 million miles out, as if slashed by an invisible blade. Some models suggest the solar wind presses against the magnetosphere here, compressing the belts inward. Others propose that Jupiter's moons, particularly Ganymede, the only moon with its own magnetic field, act like cosmic scrapers, clearing charged particles from certain regions. What's clear is that these belts aren't just a hazard, they're a laboratory. By studying how particles behave under such extremes, scientists glimpse physics that can't be replicated on Earth, from relativistic electron acceleration to plasma turbulence on scales we've never seen. Every probe that braves this zone, no matter how briefly, sends back data that reshapes our understanding of high-energy environments, both in our solar system and beyond. Until we crack the code of Jupiter's radiation, though, its belts will remain both a barrier and a beacon, a warning to spacecraft and a challenge to our curiosity. High above Jupiter's raging storms, where temperatures plunge to -150 degrees Fahrenheit, lightning crackles in a form that defies everything we know about thunderstorms. This isn't the jagged, sky-splitting lightning of Earth. It's shallow lightning, a bizarre phenomenon where bolts ignite not in water-rich clouds, but in frigid, ammonia-laced hazes so thin they shouldn't conduct electricity at all. Even stranger, these discharges are tied to Jupiter's mushballs, slushy hailstones made of ammonia and water that form like cosmic snow cones, growing as they tumble through the atmosphere. How can lightning strike in such an alien environment? And what do these mushy ice bullets reveal about Jupiter's hidden weather machine? The mystery begins with Juno's microwave radiometer, which detected pockets of ammonia and water vapor floating far above Jupiter's traditional storm clouds. At these altitudes, the air is too cold for pure water droplets to exist, but ammonia acts like atmospheric antifreeze, mixing with water to create a slushy, electrically charged soup. When turbulent winds loft water vapor high enough, it freezes around ammonia crystals, forming soft, semi-solid pellets mushballs that collide and exchange electrons, building up static charges just like hailstones do in Earth storms. But here's the twist. Unlike Earth's lightning, which flashes between oppositely charged regions of a cloud, Jupiter's shallow bolts seem to erupt horizontally, skimming along these ammonia-rich layers like sparks across a conductor. What makes this process so baffling is the energy required. Lightning needs a steep voltage gradient to jump gaps, yet Jupiter's upper atmosphere is staggeringly diffuse, more like a wispy cirrus cloud than the dense, churning thunderstorms we're familiar with. One theory suggests the mushballs themselves are the key. As they grow, they might create microscopic charge imbalances, with lighter, positively charged ice crystals rising while heavier, negatively charged slush pellets sink. This separation could generate just enough friction to spark those high-altitude flashes, even in thin air. Another idea proposes that Jupiter's powerful magnetic field plays a role, inducing currents in the ammonia haze like a planetary-scale Tesla coil. The implications stretch beyond Jupiter. If mushballs and shallow lightning exist here, they might thrive on ice giants like Uranus or Neptune, or even on exoplanets with ammonia-rich atmospheres. These discoveries force us to rethink what constitutes a storm. On Earth, lightning is a side effect of water's unique properties, but Jupiter proves that entirely different chemistries can produce equally dramatic discharges. It's a reminder that nature's creativity dwarfs our imagination, turning what should be a frozen, inert layer of atmosphere into a theater of electric marvels. Yet puzzles remain. Why do some storms produce shallow lightning while others don't? How do mushballs dissolve or evaporate before reaching lower altitudes, leaving no trace for telescopes to spot? Every bolt flickering in Jupiter's high hazes is a clue, a fleeting glimpse into the untamed physics of alien weather, where even the most familiar forces wear strange and unexpected faces. When you picture planetary rings, you likely imagine Saturn's gleaming bands of ice-hard, reflective surfaces that glint like cosmic diamonds. But Jupiter's rings play by entirely different rules. Instead of solid chunks, they're made of something far stranger, particles so lightweight and porous they'd float like dust motes in sunlight. These aren't icy boulders, they're more like cosmic fairy floss, a fragile haze of material that shouldn't exist under the brutal forces of gravity and radiation. So why are Jupiter's rings filled with these mysterious, fluffy particles? And what do they reveal about the hidden violence unfolding around the solar system's largest planet? The first clue came from spacecraft like Galileo and New Horizons, which slipped past Jupiter in the 90s and 2000s. Their cameras captured the rings in unprecedented detail, showing not the sharp, defined edges of Saturn's system, but a diffuse, almost ethereal glow. When scientists analyzed the light scattering off these rings, the data told a bizarre story. The particles weren't dense ice, but loosely packed aggregates with more empty space than solid matter. Imagine a snowball that's been crushed into powder, then sculpted into a sponge-like web. That's the structure of Jupiter's ring material, delicate, fragile, and utterly unlike anything else in our solar system. What could create such odd particles? The leading theory points to Jupiter's vicious environment. The planet's immense gravity turns its immediate surroundings into a shooting gallery, where micrometeoroids, tiny space rocks no larger than grains of sand, constantly pelt the 4 small moons orbiting within the ring system: Metis, Adrastea, Amalthea, and Thebe. Each impact blasts plumes of dust off these moons' surfaces, but Jupiter's radiation belt immediately goes to work on the debris. Charged particles, accelerated to nearly light speed, bombard the ejected material, fracturing it into ever smaller fragments and stripping away any icy coatings. Over time, this relentless assault leaves behind only the barest skeletons of rock and silicate particles too lightweight to clump together, yet too tough to fully disintegrate. But there's a twist. These fragile particles shouldn't last. Jupiter's gravity should pull them down into the planet within decades, and the radiation should grind them into nothingness. The fact that the rings persist suggests a constant replenishment, a cycle of destruction and renewal playing out in real time. Metis and Adrastea, the 2 innermost moons, might be the key. Orbiting perilously close to Jupiter's roche limit the boundary where tidal forces would tear them apart. These tiny worlds are likely shedding material constantly, their surfaces scoured by impacts and gravitational stress. Every new collision sprays fresh debris into the rings, while older particles spiral inward like cosmic confetti, burning up in Jupiter's upper atmosphere. The real surprise: these fluffy particles might be hiding a darker secret. Recent spectral analysis suggests they're tinted reddish-brown, a hue that matches the volcanic sulfur spewed by Jupiter's moon Io. If Io's eruptions are somehow seeding the rings with sulfurous dust, it would mean Jupiter's rings aren't just passive debris, they're a dynamic, interconnected system, tied to the planet's volcanic moon by invisible threads of magnetism and gravity. Yet mysteries remain. Why don't these particles clump together as they do in Saturn's rings? Some researchers speculate that Jupiter's magnetic field charges the dust grains, making them repel each other like same-poled magnets. Others think the planet's shadow plays a role without direct sunlight. Electrostatic forces might prevent the particles from sticking. Whatever the answer, one thing's clear: Jupiter's wispy rings are more than just decoration. They're a testament to the violence and chaos lurking in the planet's orbit, where even the faintest structures hold clues to the unseen battles raging across the cosmic stage. Jupiter should be freezing cold. Positioned 5 times farther from the Sun than Earth, it receives only a fraction of our sunlight, just 4% of the warmth that bathes our planet. Yet when scientists first measured Jupiter's heat emissions, they got a shock. The gas giant radiates nearly twice as much energy as it absorbs from the Sun. This excess heat isn't just a mild discrepancy, it's enough to power global storms, drive supersonic jet streams, and sustain atmospheric chaos that defies all expectations. Where is this energy coming from? The answer might rewrite what we know about how planets age. The leading theory points to Jupiter's violent birth. When the planet formed 4.5 billion years ago, it grew by swallowing massive amounts of gas and dust from the primordial solar nebula. As gravity compressed this material, potential energy converted into heat enough to bake the young Jupiter into a searing inferno. Models suggest this leftover warmth should have dissipated over time, like a baked potato cooling on a counter. But Jupiter's core is still piping hot, implying something is either slowing the cooling process or adding fresh heat. Some researchers propose that helium rain, a phenomenon where heavier helium droplets separate from liquid hydrogen and sink toward the core, releases gravitational energy as they fall, essentially giving Jupiter an internal energy boost. Picture drizzling syrup into a glass of water. As the syrup sinks, it releases tiny amounts of energy. On Jupiter, that drizzle happens at a planetary scale, with helium acting as the syrup in an ocean of metallic hydrogen. But there's a problem with this explanation. While helium rain might contribute, calculations show it can't account for all the excess heat. That's led to wilder ideas like tidal heating. Jupiter's massive moons, especially Io, tug on the planet with gravity, flexing its interior like a stress ball. This constant kneading generates friction, which converts into heat. Yet even this can't fully explain the numbers. The math suggests tidal forces from Jupiter's moons are too weak to produce the observed energy surplus, leaving a gap in the equation. An even more radical theory suggests Jupiter might still be contracting, as the planet slowly shrinks under its own gravity. Perhaps by a few centimeters per year, this compression could release stored energy like a cosmic pressure cooker. It's a subtle process, but over billions of years, even microscopic shrinkage could add up to significant heat. The challenge: we've never directly observed this contraction. Juno's gravity measurements hint at deep atmospheric currents that might align with the idea, but conclusive evidence remains elusive. The implications stretch far beyond Jupiter. If gas giants can retain or generate heat long after formation, it could change how we model exoplanets, especially those orbiting distant stars. Hot Jupiters, for instance, might owe their scorching temperatures not just to stellar proximity, but to internal engines we don't yet understand. Even ice giants like Uranus, which oddly emits almost no excess heat, become part of the puzzle. Why do some giants simmer while others go cold? The most tantalizing possibility is that Jupiter's heat isn't coming from one source but many, a combination of residual formation energy, helium rainfall, tidal forces, and perhaps even exotic chemistry in its deep interior. Like a bank account fed by multiple income streams, the planet's thermal budget might balance through processes we're only beginning to uncover. Until we send probes capable of plumbing Jupiter's hidden depths, this cosmic furnace will keep burning with questions we can't yet answer. One thing's certain: in the economy of planetary heat, Jupiter is running a surplus that defies every expectation. And that surplus is powering some of the most breathtaking storms in the solar system. Jupiter's southern hemisphere is home to one of the planet's most hypnotic spectacles, a flawless chain of colossal white storms nicknamed the String of Pearls. These swirling ovals, each large enough to swallow Earth's biggest hurricanes whole, line up with eerie precision along a single latitudinal band, spaced so evenly they look like jewels on a cosmic necklace. First spotted in the late 1980s, this formation has persisted for decades, defying every expectation about how giant planetary storms should behave. On a world where chaos reigns, this striking symmetry is an anomaly no one saw coming. What makes these storms so baffling isn't just their longevity, it's their refusal to merge or drift apart. Jupiter's atmosphere is a battlefield of colliding tempests, where smaller vortices are routinely consumed by giants like the Great Red Spot. Yet the pearls, each over 5,000 miles across, maintain their delicate spacing like dancers holding perfect formation. Some researchers compare them to traffic on a freeway, where invisible rules of the road prevent storms from crowding one another. But what could those rules be? One clue lies in the powerful jet streams flanking the Pearl chain. These eastward and westward winds, racing at over 300 miles per hour, might act like atmospheric guardrails, herding the storms into place and preventing them from straying. The Pearl's uniformity raises even deeper questions. Why are they all nearly identical in size and brightness? On Earth, storms vary wildly in strength and lifespan, yet Jupiter's pearls appear cloned from a single template. Some theories suggest they're fed by a shared energy source, perhaps plumes of moist gas rising from deep within the planet, punching through the cloud tops at regular intervals. Others propose they're self-sustaining, their spacing governed by a natural resonance frequency in Jupiter's atmosphere, like standing waves in a vibrating string. Imagine blowing across the top of a soda bottle to create a tone. Jupiter's winds might be doing something similar, but on a planetary scale, playing the atmosphere to produce these perfectly spaced storms. Even their color is a puzzle. Unlike the great red spot's crimson hue, the pearls gleam white, suggesting they're rich in ammonia ice, a compound that typically forms higher in Jupiter's atmosphere. This could mean the storms are unusually shallow, drawing their energy from upper atmospheric layers rather than the planet's depths. Alternatively, their brilliance might come from towering cloud tops, so high and cold that sunlight scatters off them like fresh snow. Data from NASA Juno spacecraft supports this idea, revealing that the pearl's roots don't plunge as deep as other Jovian storms, making them more like icy caps floating on a turbulent sea. The most tantalizing question of all, are these storms immortal? Some models suggest the pearls could be ancient, their formation tied to a global atmospheric upheaval centuries ago, perhaps even the same event that birthed the Great Red Spot. If true, they're not just weather, they're living fossils preserving clues about Jupiter's climatic past. Other simulations hint they might be temporary, appearing and vanishing in cycles we've yet to map. Every new image from Earth-based telescopes and orbiting probes adds another piece to the puzzle. But for now, the string of pearls remains a mesmerizing mystery, a reminder that even in the wildest corners of our solar system, there's an order hiding within the chaos. Jupiter should never be silent. As the solar system's most boisterous radio broadcaster, the planet constantly crackles with bursts of kilometric radiation, electromagnetic waves so powerful they've been detected from Earth for decades. These emissions pulse like a cosmic metronome, synced to Jupiter's rotation, creating a rhythmic radio heartbeat that astronomers once thought was as reliable as clockwork. But there's a catch. When Jupiter's night side faces Earth, this noisy signal vanishes entirely. The planet goes radio dark with eerie precision, as if someone flipped a switch. No gradual fade, no static whispers, just silence. What could possibly mute the solar system's loudest radio source every time it turns away from the sun? The leading suspect is Jupiter's magnetosphere, a colossal magnetic bubble shaped by the planet's rapid spin and Eo's volcanic fallout. On the day side, solar wind compresses this bubble, squeezing magnetic field lines until they snap like overstretched rubber bands, releasing energy as radio waves. But on the night side, the magnetosphere stretches into a long tail, millions of miles of tangled magnetic currents where particles might be escaping rather than colliding. Without those high-energy collisions, the radio emissions could simply fizzle out. Think of it like a neon sign. Electrify the gas and it glows, cut the power and it goes dark. Jupiter's night side might be experiencing a similar blackout, its particle accelerators temporarily offline. Yet this explanation isn't perfect. Some models suggest the solar wind shouldn't have that much control over Jupiter's radio output, given the planet's immense magnetic independence. Alternative theories point to Jupiter's ionosphere, the electrically charged layer of its upper atmosphere. On the day side, sunlight ionizes atmospheric gases, creating a conductive shell that reflects and amplifies radio waves. But when darkness falls, this layer could dissipate, breaking the circuit. It's like losing cell service in a tunnel. The signal isn't gone, but the path to transmit it has vanished. The plot thickens with data from NASA Juno spacecraft, which orbits Jupiter pole to pole rather than along its equator. Juno's recordings reveal faint, disorganized radio whispers on the night side, nothing like the day side's booming broadcasts, but enough to prove the silence isn't absolute. This hints at a more complex story. Perhaps the emissions don't disappear so much as scatter, their energy diffusing into frequencies our telescopes can't easily detect. Or maybe Jupiter's magnetic field lines, twisted by the planet's lopsided interior, funnel radio energy toward unexpected directions, like a flashlight beam aimed away from Earth. Then there's the wild card, Eo's role in all this. The volcanic moon pumps Jupiter's magnetosphere full of plasma, but its position relative to the night side might alter the recipe for radio waves. When Io orbits into Jupiter's shadow, its volcanic gases temporarily stop ionizing, potentially starving the magnetosphere of fresh particles right when the night side needs them most. It's a celestial domino effect. No sunlight means no eoplasma, which means no radio glow. The implications stretch beyond Jupiter. If a planet's radio emissions can flicker on and off like a cosmic strobe light, it could reshape how we search for exoplanets. Astronomers often listen for radio signals as signs of alien magnetic fields, but what if those signals vanish for half a day? Jupiter's night-side silence is a cautionary tale, reminding us that even the loudest planets might whisper when we're not looking. Until we park a spacecraft on Jupiter's midnight side, this radio blackout will remain one of its most haunting mysteries, a reminder that even giants have secrets they only share in the light. From the churning depths of the Great Red Spot to the ghostly whispers of its vanishing radio signals, Jupiter has proven itself a master of cosmic illusion, a planet that dazzles us with answers while guarding its deepest secrets. We've peeled back layers of its storm-wrapped enigma, uncovering 25 mysteries that defy explanation. The lopsided magnetic field warping space around it, the silent dark lightning cracking through ammonia clouds, the eerie geometric dance of polar cyclones, and the missing mid-sized moons that hint at ancient celestial violence. Each discovery feels like turning a page in a thriller where every clue leads to two new questions. What's startling isn't just how much we've learned, it's how much still looms in shadow. We've sent probes through Jupiter's radiation maelstrom, mapped its gravity with atomic precision, and watched its auroras blaze brighter than cities, yet the planet's core remains a fuzzy phantom. Its atmospheric energy budget a riddle, its ammonia conveyor belts and helium rains still theoretical sketches. Even the Juno mission, which rewrote textbooks, left us staring at day to spikes that whisper of processes we can't yet name. Perhaps that's the real magic of Jupiter. It refuses to be pigeonholed. Just when we think we've categorized its storms, it unveils shallow lightning. The moment we model its rotation, it reveals differential spin. It's a celestial shapeshifter, daring us to rethink not just gas giants, but the fundamentals of planetary science. And with missions like ESA's JUICE and NASA Europa Clipper preparing to probe its icy moons, we're on the brink of revelations that could redefine life's potential in our solar system. So here's the invitation: join the hunt. Maybe you're captivated by the string of pearls' hypnotic symmetry, or the way Eo's volcanoes electrify Jupiter's auroras like a cosmic defibrillator. Perhaps you're itching to solve the radio blackout or decode the stratosphere's unexpected chill. Drop your favorite mystery in the comments, or better yet, pitch the mission that could crack it. Because Jupiter's greatest lesson isn't just about one planet, it's about humility. In a universe where even our neighborhood holds worlds that baffle us, curiosity isn't just a trait, it's our compass. The next chapter of discovery isn't just written by scientists in labs, it's waiting in the questions we all dare to ask. After all, the universe's most thrilling stories aren't the ones we've solved, they're the ones that still send shivers down our spine.